All right, we're going to do a few more examples um, of these set theoretic descriptions. Um, they'll be familiar. So R is a field. What happens when we add I to R? Well, we need access to any real number, but we also need access to the imaginary number I, and any real number times that imaginary number I, and any combination of a real number and a multiple of the real number times the imaginary number I, where A and B is in R. Ah, what is that? That's exactly equal to the complex numbers. All right. How would you show this? Well, R adjoint I is clearly going to contain A plus BI, right? It has to have that. On the other hand, this is the maximum any subfield of C can be, because this is just all of C. So it's certainly a field, right? This guy in the braces is certainly a field. And so it must be equal to R adjoint I. Okay, so that's an example that should be familiar. 2, we looked at this Q adjoin root 2 example already. Well, we didn't prove the set theoretic description, but we could. How do you prove it? Well, you do exactly what we just did. You show that this is the right-hand side's a field, and then you show that the left and right-hand sides contain each other. Okay, great. Let's do a slightly harder example. We might be so the number of rational coefficients that we can have in these expressions, or base field coefficients in this other case, isn't always like 2 or 4 or something like that. It can be an arbitrary number. Let's take Q and let's adjoin the real cube root of 2. And let's call the cube root of 2 alpha. It's technically it's convenient to give it a symbolic name for algebraic computation. So we're just going to call it alpha. We might be tempted to say, oh, I need P plus Q cube root 2, or Q alpha rather, and then to stop there. But it turns out that you actually need to have an alpha squared. You have to also throw in the cube root of 4. And so let's see that real quick. Let's show that alpha squared is never equal, well, is not in this set. Is not in the set of P plus Q alphas, where P and Q are in Q. So you do actually need to throw in, I'll put it in green, an R alpha squared here. Because if you don't have that, you don't have access to alpha times alpha. We're going to show it's not here. Okay? Right. Well, how do you show something is not there? Well, you suppose it is, and you find a contradiction. So suppose that alpha squared is of the form, I'm going to keep with the book's notation here, J plus K alpha for some J and K in Q. Okay. All right. Let's go ahead and multiply this through by alpha. When we multiply on the left-hand side by an alpha, we're going to get an alpha cubed. Okay, so we're going to multiply through by an alpha. We're going to get alpha cubed. Alpha cubed is 2 because alpha is a cube root of 2. And on the right-hand side, we're going to get, what are we going to get? We're going to get alpha j plus alpha squared k. Great. But alpha squared, we're assuming, is j plus k alpha. So we're going to plug that in. Did I do that right? I think so. That looks good. Okay. And then we're going to get alpha j plus jk plus k squared alpha. So I think we get jk plus, let's see, j plus k squared alpha. Whew. Right, let me just underline jk, and then we have the j, and then we have the k squared. Okay, everything works out. Cool. And on the very left-hand side, we have a 2. Okay. So what this is telling us then is that 2 minus jk is j plus k squared times alpha. And The right-hand side has a cube root of 2 in it. The left-hand side is just a rational number because j and k are rational. And so the only way that a cube root of 2 is going to be, the only way that this can work is if both sides are 0, because the cube root of 2 is irrational. All right, so this gives us two equations. It tells us, this is a 2, not an alpha. It tells us that 2 is jk, and it tells us that k squared is negative j. All right, let's solve this. I think this first guy we can write as 2 over k is j, and then we can plug that into the second one. K squared is negative j, so it's negative 2 over k. So this tells us that 2 over k is j, and k cubed is negative 2. And keep in mind, j and k are rational numbers, and so this is saying that k is a cube root of negative 2. And it's saying that that's a rational number, which is a contradiction. This is false. Cube root of 2 is irrational. All right, what have we contradicted? We've contradicted that alpha squared can be written as j plus k alpha. So namely, you do have to throw in this r alpha squared. So this is the correct description. You can't get away with, when you have a cube root, with just throwing in the cube root. You also have to throw in the cube root squared. Similarly, a similar argument shows if you have a fifth root or a sixth root or a seventh root, you usually have to throw in all powers up to 7, and that's something that we'll formalize when we bring in the polynomial ring description of these sets.